Okay, Assalamualaikum. So we continue with chapter 6, part 4. So we continue with this assembly of actin filament, or I repeat this assembly of actin filament because before this is interruption. Okay, so we have the assembly of actin filament. So that the principal component of thin filament. Okay, so we have the D-actin, that is globular protein, a sphere protein, and F-actin, the previous protein. Okay, so these are the fibrous protein. Okay, so here you can see that these are the protein, and this, let's say, these are the highway of our messenger, or the 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 movement, the working, the working protein. Okay, so here we see this. Okay, so we have the construction of actin filament. So we have this 5-step model: A plus A, A2, A plus A2, A3, A plus A3, A4, A plus A4, and so on, N, and A plus N equal to N. Okay, so here these are the left hand side reaction rate constant, and these are the left hand side rate reaction. Okay, so these are association, and these are dissociation. So we can see that the rate of association is greater than the rate of dissociation. Okay, so and when n, A plus A4 become n, so we can see that these are becoming the non tidak balas tidak berulang. Okay, so these are the not going back to it. It's going back from left. It's go from left to right, but it will not be right to left. But as we see, these are 0, but it's supposed to be 0.001, so we can ignore this dissociation. Okay, so here we can see that the association also depend on the average length of the actin filament. Okay, so on purity and monomer concentration during the polymerization. Okay, so it's a pure actin filament, so there will be a lot of association. Other will be less association. Okay, and the actin monomer in concentration during polymerization varied as indicated. Okay, so this one, the filament formed during each 30 millisecond interval were allowed to elongate over the sustained course of the reaction. Okay, and these are the two singly gel treated actin and double gel treated actin. Okay, so we can see that here double gel treated actin reach saturation much faster than the singly gel treated actin, and in this case the length of the actin chain is about 2500 molecule. Okay, and the theoretical length calculated by kinetic simulation using the nucleation and integration model and the rate constant in the text without anything, parameting dash, and with both anything and parameting. These are solid, and this one is the explanation for this. Okay, so the chain of concentration, so when it associate, dissociate, then there will be a different or the change in concentration for each molecule, okay, or each element. Okay, so Ka is annealing rate, Kf is fragmentation rate. Okay, so looking at this, writing it, the rate change dn dt over Ka4 A4 minus Kn squared plus Kf n. Okay, so we can say that the rate of annealing goes down when the filament become longer because as I said in the previous slide, when the filament become longer, so the the free ligand or the free protein need to uh, diffuse more so that it can find the binding site to the uh, attached to the filament. Okay, and if the rate constant is a division limited rate constant, so the transverse division is controlled by the mass of the polymer and the density of the polymer network. Okay, so uh, this one depend on this polymer. Okay, so what we can say is that when the polymer network is much become longer, then uh, it it uh, moves slowly, and then it making that the free ligand or free protein can attach it much faster rather than the short, making that it can move freely. Okay. Okay, so these are the diffusion constant along the tube is inversely proportional to the length of the filament. Okay, so if you increase the filament, you can see that the diffusion constant will be smaller. Okay, it will be smaller, meaning that it will the long filament will move much slower. So the Ka diffusion limited constant can be written as this equation. Okay, so we know this, so we can find this Ka diffusion. Okay, so these are the association rate. So what is about the dissociation rate or the fragmentation rate? The number of rod within a distance b of a given rod is b l squared n. Okay, the number of rod between the n distance, the distance. So the kf can be written as kf equal to kf1l plus kf2l squared n. Okay, so these are the filament A, and these are the filament B. Okay, so if both associate, will produce another rate constant. Uh, so here we have this equation. Okay, so the rate chain of n become dn dt. Okay, uh, the number of element. Okay, so from this equation, or we can move it as this one. So the P is among the polymerase protein. So A plus A minus A minus A minus 2A squared. This is my A1. A1 2A2 minus 3A3 minus 4A4. Okay, so this meaning that how much protein long is the protein. Okay, so if the actin concentration increase, and more protein will polymerize, because as we know, when we meet much uh, frequently, so then there will be the association. Okay, so the rate of annealing decrease by the fragmentation rate increase. Okay. Okay, so these are the okay. So in this case, the rate of annealing decrease. So the rate of fragmentation decrease. So these are saying that the long filament become much shorter, shorter, and shorter, and shorter. Okay. Okay, so that is the assembly of sample of assembly of microtubule. Okay, so next or the last one is the muscle contraction. So how can we make the muscle to contract? Okay, so using this biology knowledge. So a muscle is composed of a large number of fiber that can be contract under direct stimulation of nerve. Okay, so by putting the stimulate or the ATP, so it can this fiber or this muscle can uh, contract or uh, this contract. Okay, so a muscle is connected to two bones across a joint and is attached by a tendon at each end. Okay, so the contraction of a muscle produces a pair of reaction force between each bone and muscle. So kalau kita muscle kita contract, so kita boleh mengangkat. Okay, the work W performed by a contracting muscle is W equal to sigma A delta L. So where A is torsion section of our muscle, L is the shortening distance. How short can be the the muscle can contract, and sigma is the tensile stress produced by the muscle. Okay, so it needs to do. Okay, and the power from our physics, P equal to sigma A V. Okay, V is the uh, process. The volume. Okay, the velocity. Okay, the velocity of the movement. Okay, the power depend only on the value of cross sectional area. Okay, so here these are. Okay. Kalau A berubah, the power also change. Okay, then contraction velocity V equal to B F max minus W over W plus A. A and B is constant. F max is the maximum force. V is the weight for pemberat yang kita nak. So the maximum velocity of for zero load V equal to V max equal to V over A F max. Okay, so yeah, this one 0 0. So the maximum velocity is just this equation. Okay, so here these are the force. So max. Okay, so here we can see that the maximum force that we can do after this line, meaning that the weight is too heavy, we cannot contract or we cannot lift it using our muscle. Okay, so these are the muscle, the picture or the diagram of the muscle. So this here we have the muscle. In the muscle we have the fasciole, and next we have nuclei, and we have inguinal muscle or the cell, fiber cell. Then we have submarine, and then we have the microtubule. The microtubule, that is, let's say, the microtubule. Okay, so these are the, so every of these will contract. Okay, so to make this muscle or tangan kita ni mengangkat atau menurun. Okay, so here again the component of the muscle. So this we have the muscle. In the muscle we have the fiber 0.4, and in the fiber we have this Z band and Z band. So we have the myosin here, and we have the actin. Okay, so here you can see that by changing the length of this actin. Okay, so we can make our muscle to contract all this Okay, so here again how the muscle contract. Okay, so thick filament myosin, thin filament actin. Okay, so here we can see that uh, this one will contract. So and this also uh, this one will making the this, let's say these are the connection to move near to each other or far from each other. Okay, so these are the again the diagram of the muscle contraction. So here we can see that if we start with this one. Okay, number one. Okay, so formation of cross H. Okay, so actin one using the ADP. Okay, so this uh, is cross bridge. You can see that it will move because of ADP, so it will move or change the configuration. So this actin also will move to the front, and when it come to the front with the ATP, so ATP will make back this cross bridge to contract or to become L shape and release this actin, and after some time so it will be produced back ADP. So you can see that here the actin filament can move to this side, to the left. Okay, and this will be repeat again and again so that this actin can move to this left side or right side. Okay, so these are the uh, step by step of this diagram. Okay, the theory of skeletal muscular contraction. The impulse reach neuromuscular junction acetylcholine because diffusion wave due to a large influx of positive ion. Action potential spread across plasma membrane down to the tubule. Calcium is released from sarcoplasmic reticulum, and the calcium bind to troponin. Then it will making that conformation in the tropomyosin occur and move of the hotspot of actin. So the actin myosin complex is together after splitting of ATP of the myosin, and the high energy myosin head swivel pulling actin inward in a power stroke, and ATP is released from the myosin head. Myosin and actin remain complex. ATP bind to myosin and release the actin. Okay, so here we can see that step by step of this uh, cycle. Okay, this cycle. So how my actin and myosin can, or the myosin can. Okay, so here again this, you can see that it move, and another example. So rigor mortis is a state in which neither ATP or no calcium ion is present, and the myosin head are bound to actin. The state occurs when ATP is present, but uh, ion this uh, calcium ion is not, so myosin head are not bound to actin. And conversion state is when both ATP and this ion are present, and myosin head are bound to the actin. Okay, so we have this. Okay, so here you can see that this we have the ion, calcium ion. So we make this myosin to attract to this or attach to this actin. Okay, so moving like this. this configuration to this compo. Okay, so will be again and again. So that's all for this chapter number 6.